Now we shall be looking into the concepts that how we could actually make an ammeter with the use of a galvanometer, right? We will be looking at step by step so as we could really understand at every step that what we are doing and how we are doing. First of all, let us take a galvanometer. Say for example, this is a galvanometer, right? Now this galvanometer will obviously have its own resistance, because as we have seen in the setup of a galvanometer, the frame that was over there or the windings or each and everything obviously that has got its own resistance. So say for example we have connected this galvanometer with a circuit. The current is flowing through it. The current flows through it is I. Okay? And this galvanometer, as we know, that it is very sensitive to the current being passed. So whenever it will see a small amount of current that is being passed through it, it will just give a deflection. So here comes the limitation of a galvanometer. The limitation of a galvanometer is that, first of all, if we do take that if G is equals to, say for the resistance of galvanometer, this will actually give its full deflection for say an amount of current only Ig. Ig equals to maximum current for which the galvanometer is sensitive, because if only it is sensitive, then only it will give deflection, right? Now if it is said that over here the I that is flowing through it, if it is already been said that I is greater than Ig, then say for example the value of I is 100 ampere and Ig is only 10 ampere, so the galvanometer will give the deflection only for 0 ampere to till 10 ampere till Ig, right? After 11th ampere till 100 ampere, this galvanometer will not be sensitive. I mean, this will be sensitive, but there will be no deflection in the scale. Or there may be deflection in the scale, but that will be surely an absurd readings, not on that I is directly proportional to A. Now, so for this, where I will be greater than Ig, what we need to do is that we need to bring down the sensitivity of the galvanometer. This sensitivity of the galvanometer, as we have seen, that it was equals to alpha divided by I, and we have seen the value of alpha divided by I was equals to simply as NVA divided by K. So if we are, say for example, reducing the values of N, B or A, or if we are increasing the value of K, then the sensitivity shall decrease. Then only this Ig, or the maximum current for which the galvanometer is sensitive, this will go up. But wait, this is not the solution. We are devising some ammeter, and for that particular reason we are decreasing like the efficiency of the galvanometer. We are decreasing its sensitivity. It is not a point. Obviously we cannot do so, because this is not practical. So what we need to do is that we need to keep the efficiency or the sensitivity of this galvanometer fixed to its point Let us not decrease the sensitivity, but we have to devise something so that in the whole like apparatus of the ammeter, this entire current flows through. Say for example, it is said that only Ig can flow through this galvanometer. Okay, not a problem. And it is said that Ig is very, very small. If this is the scenario, we see that we are passing I, but only the maximum current for which it will be giving reading actually for the sensitivity is Ig. Then as per junction rule, we will make some amendments in this apparatus. How? Let us take a point from over here, and in the parallel we keep a resistance, and if we are able to do so, obviously as per the junction rule, this current that will be flowing will simply be equals to I minus Ig. Then only I minus Ig plus Ig will give us the value of I. And this resistance is called the shunt resistance with the value of S. Why is it shunt? We shall be coming just now. But for the time being, it may be noted that the shunt resistance has a resistance which is very low, right? So we can say that S is the shunt resistance, which is obviously very low, right? Now, if this is basically very low, then I minus Ig, which is the bigger part of this I, will flow through this, right? So we have made as such the parallel thing. Now, what should be the value of S for a given I? We need to find out. Because, say for example, if we are attaching any amount of S, it may be seen that the total I minus Ig may not flow into this, or else we can also see that the major portion of the I is flowing through it and Ig will be smaller as it could take the maximum value for, right? So, over here what we can see, if this is a parallel combination, as we know from current electricity, that in this parallel combination, the potential difference across these 2 points, for example, this A and this B, the potential difference across these 2 points will be V, say for example. So the potential difference across for the galvanometer and across for the shunt resistance, it will be the same, right? Now what is the potential difference for this, say, galvanometer? If we define out for galvanometer, ED, or the potential difference, is equals to V. So we can write V as equals to Ig, the amount of current flows through multiplied by the resistance of the galvanometer as per Ohm's law. So this will be V equals to Ig multiplied by G. Let us give it the first equation. Now secondly, we know that for the shunt resistance, which is connected in parallel with the galvanometer, for shunt resistance or shunt resistor, we could say, the potential difference across the point A and B will simply be again BV, right? Because this is a parallel combination or the series combination. So for this, the V will be I minus Ig, because this is the amount of current which is flowing through the shunt resistor, and the value of this resistance is S. By Ohm's law we can make this second equation. Now you see that both are, this is V equals to this and this is V equals to this, so we can equate their right hand expressions. So from equation 1 and 2 we shall be getting as Ig multiplied by G will be equals to I minus Ig multiplied by S, or in other terms we can come out with the expression for the value of this shunt resistance as S equals to Ig multiplied by G divided by I minus Ig. So now we have got the value of this shunt resistance, what the amount of this resistance should be. Now, wait, we know G? Yes, we know it. We know Ig? Yes, because for a given galvanometer, we know that what will be the maximum current for which this galvanometer is sensitive. So we know Ig. Do we know I minus Ig? Obviously, if we don't know that what is the value of the current we need to pass through, the maximum amount of current what we need to pass through. Because for this certain apparatus we have devised that okay, we need a device which could measure from 0 ampere till 100 ampere. So I value will be 100 ampere and Ig again we know the value. So we know the values of all this expression on the right hand side. So obviously putting their values as in this term, we should get the amount of S. And for this amount of S, for this S, the galvanometer or this total apparatus now, let us say that this apparatus, let us mark it as the area from this hole, right? And this is basically known as ammeter. Now why it is ammeter we are coming later on. So we can say this for this particular amount of S, the ammeter is now sensitive for 0 ampere to I ampere values. Say for example, we are passing over here the current of I by 2, at that same time also no need to worry, with this value of shunt resistance we can do so. But yes, obviously if this value is greater than I, then there will be mismatch. And that is the reason why we need to understand and we need to find out the value of this shunt resistance. Now this value of shunt resistance is very low, as we know, okay? And since this is a parallel combination, as we could see in this ammeter, this is a parallel combination. So we can say over here that the effective resistance of this total, like this, the apparatus being made of this ammeter, will simply be equals to this. This will be G, the resistance of the galvanometer, multiplied by the shunt resistance, that is S, divided by G plus S, as this is a parallel combination of two resistances, right? And as we know that if we are going to make a parallel combination of say two resistances, their effective resistance what we shall be getting will be lesser than both of them. Say for example, the amount of this G is equals to 100, the amount of this S equals to only 1. In that case it will be 100 multiplied by 1 divided by 100 plus 1 will be equals to 100 divided by 101, which means it is lesser than 1. If it is lesser than 1, obviously it would be lesser than this S as well as this G. Because this was 1 and this was 100. right? So what we got to know from over here is that in this apparatus we made, the effective resistance will be lesser than G as well as S. And if we make this shunt resistance very low, then obviously the effective resistance will be very low. Now, say for example, we devise over here, this is say a circuit. Say for example, this is a circuit now, and over here there is a bulb, and over here there is a battery, and this is as such, and this one is the ammeter. So this ammeter is basically this entire thing, right? And if we do devise this ammeter inside this, we will notice that this ammeter is basically being connected in series to this circuit. Now, why these ammeters are actually they are placed in series in the circuit? This answer is over on this line. Because the effective resistance is very, very low. And if the effective resistance is very, very low, so it would not hamper the I that is flowing through it. It will remain the same as it is. Right? So over here we have seen that how we could devise an ammeter with the help of a shunt resistance going in parallel with the galvanometer, such that we need not to bring down its sensitivity of this galvanometer to a lower one, and at the same time we have understood that why actually the ammeters are being placed in series with the circuit, because their effective resistance is very, very low, right? Thank you.